Section 2.8, we're wrapping up Chapter 2. There's not going to be a lot of writing in this video, just basically walking you through, I guess, some expansions of the concepts we've seen so far. Go ahead and get started. Our goal here is to see the derivative as a function and how it could help. And how it could help doing so, right? How doing so can be helpful for us. So we've already defined the derivative at a given point A, but like I said before, one thing that is beneficial is to avoid choosing a point A and doing the math with unknown A. And so we call it x. And that way you can find another function f prime of x, the derivative of f, without having to assign a point to it. And that's how we call this function f. It's defined in the same way, except you don't put a point, right? You just use it. We have a geometric interpretation for f prime of x, so it's the slope of the tangent line to the graph of f at that point. And we call the derivative because it is derived, right? We start with f and we derive it from through this process from f. Okay. The domain is going to be new, a different domain, because there will be points where the limit that defines the derivative does not exist. So the domain is simply the points, the set of points where the limit exists, where f prime of x exists, and it may be smaller than the domain of f. So here's our first example. We have f of x graphed here in blue. And then what you can do is try and understand how the graph of f prime of x can be obtained. And look at the most important points here. At this point, for sure, the tangent line is horizontal. So it has slope equal to 0. So there, f prime of x crosses the x-axis. Same here. Yeah. Same here. Whenever the slope of my tangent line is 0, which means to say my tangent line is horizontal, f prime is 0. So it can graph it as a function for each x value. Okay. Now for p, you can just calculate this by drawing the tangent line, and this is just a guessing work using maybe straight edge, but you can just calculate it by hand if you're given the formula to find what's the height, right? So m here was 3 over 2, so you actually have to look at the height. This is 1.5 because you're looking at the slope at each point and you're building a new graph from those values. Okay? Another thing that's noteworthy. Note here, in this first strip here, in this part of the graph, do it differently. The graph here is going down, right? So that means the slope is negative. For any line that you draw, any tangent line that you draw, the slope is negative. So that means your graph for f prime has got to be under the x-axis. Okay? Here for this other part, we're going up. So now my graph has got to be positive. Even if it goes up or down, my graph is positive. Okay? The y-coordinates are positive. So here, f starts to go down again. So now the slope of the tangent lines are all negative. So f prime has got to be under the x-axis. Same thing. Now it's going up. F prime has got to be above the x-axis. So pay attention to those things. Try to understand what I'm even trying to say here. We're basically drawing a new graph where the y-coordinates are the slopes of the tangent lines from the original graph. That's what we're doing. Okay, so trying to understand what's going on. Let's move on and talk about more things. We have, I guess, a little expansion on what I was doing. And I guess the observation that positive slope, negative slope and zero slope that I mentioned. Look again at another example here. F of x equals square root of 0, square root of x, excuse me. So that's square root of x. If you do that limit that we used to do to find f prime of x, you find this. And when x gets close to 0, this is 1 divided by something very, very small. So the result is very, very large. So you get the derivative being very large here, right? And that, if you zoom into this, you can see that, right? This is getting very close to a vertical line, to a vertical graph. You can zoom in further if you want, and you can see this is very, very, f is changing very fast here, which is a consequence of the fact that the derivative, right, is getting larger and larger. You can see that through this line, through this equation here as well. Okay? Try and understand the concepts that we're talking about. So we have, when x is large, f prime is very small, and it's corresponding, and this corresponds to the flatter tangent line. So you can see here, as you go closer this way, right? The tangent lines, this is f prime, right? This graph on the side is f prime, so it's getting closer and closer to 0, which means to say the tangent lines as we go this way are getting more and more horizontal with smaller slope. Okay? So it has to do with this horizontal asymptote that we have on f prime. F does not have a horizontal asymptote. F does not have a horizontal asymptote, but f prime does have one, which is this. Y equals 0 on f prime. Okay, so we're building a new function from f, and this new function is f prime of x, which is its derivative. Okay? We're going to see how that's important, how useful it is. Talk about useful other notations. Historically, people have come up with the idea of derivative differently and at different places. In Europe, for example, you have two very famous Isaac Newton is the famous mathematician who came up with this notation, f prime of x. But there's another way to write it, and that's dy dx. Okay? And that's called Leibniz notation. I'll write it soon so that you can keep an eye on it. It means the exact same thing. The difference is that this is how Leibniz wrote it, which is this German mathematician, who also came up with derivatives using limits more or less at the same time as Newton did. But because Newton was more famous and more well connected, I guess, better connected, the first notation became the most common. But eventually you're going to see these other notations. So they all mean the same thing. They all mean the same thing. This last one has its own advantages if you go and study multivariable calculus. But just try and remember, it's called like the differentiation operator because you can just place it, right? It's like d dx of f, and it's going to be df dx. Just you can think of it as an operation that you do on the function, and you call this differentiation, right? This operation. Okay? So to differentiate a function is to find its derivative, calculate its derivative. Okay? Got some other, so this is the name of the guy I was mentioning before. This is Leibniz. Again, German mathematician who was not very well known in his time until this became more useful and more widespread. And its notation is suggestive again because the dy comes from the change in y, the delta y. Delta is the Greek letter that's equivalent to d, right, in our alphabet. And same for dx, delta x. So the delta changes into a d. Okay? So that's where Leibniz came up with this idea, how he came up with this idea. Newton was more abstract thinking. There you go. So sometimes you want to know where dy dx is at a given point. So you put this little bar, which means to say simply plug in a. okay, into x. You can do this too. You have to be able to recognize all these notations because the book may use them. If you go study at a different place after this with a different teacher, they may be more fond of this different notation, this Leibniz notation, or they may use a different book. So you have to be able to use this. This bar here just means that, right? And in calculus too, this little bar is going to make an appearance as well. All of this, these two things, they mean the same thing as f prime of a does, okay? So, just said that finding the derivative is also called differentiating, right? Differentiation, or differentiating a function, right? So we say that a function is differentiable at a if we are able to find its derivative. So if the derivative exists, then we say f is differentiable at a. If we just say it's differentiable without saying where, it's differentiable everywhere. Or we can say it's differentiable at an interval, right? If it's differentiable at every point in that interval, okay? Just using words to say things that we already are able to say mathematically. Okay, so here's the first example. Where is the function f of x equals absolute value x differentiable? So if you remember the graph of this guy, this is what it looks like. It's got a little, I guess, sharp turn here that some people refer to. There's a word called cusp that refers to this sharp turn at the point 0. And if you think about looking at a tangent line, there are many possible lines that you can draw. Like this one here touches at a single point. This one here touches at a single point. This horizontal one touches at a single point. There are many different lines that you can draw at that point 0, 0 that would be thought of as tangent lines. So you don't have a choice, a clear choice to make. So as a consequence of this, when you do the math, you're going to see that the limit does not exist. So f is not differentiable. F prime of 0 does not exist. Okay? So you're going to see that here. They're going to do, when x is positive, f prime of x is 1. And they just do the math using the limits and the ideas that we've been able to use. Okay? Use the fact that absolute value of something positive is itself. So we can just get rid of the absolute values. And if you do the same for when x is negative, the absolute value of something negative is minus that thing. So you get minus 1 as the result. F prime of x is minus 1. However, if you were to graph this, or you can just look at 0, the idea is that you try on the left limit when h goes to 0 from the left and from the right, and you get different values. So if you were to graph it, you would see there's no way you could find a derivative at 0. Just look back at this again. If you need more clarification, the idea is that you're trying to find the limit when h goes to 0, and the limit is this, and you end up with an absolute value. So let's break it apart and look at the two sides. Look at the right side. This is this. Absolute value of h when h is positive is h itself. Absolute value of h when h is negative is minus h. So you get two different things. So the left limit is not the same as the right limit, and therefore the limit does not exist. Therefore the derivative at 0 does not exist. Okay? So that's one function that's not differentiable at a point. Not all functions will be differentiable, as you can see from this example. Remember the graph. Okay? And the fact that geometrically you would be confused when trying to find a tangent line. There are many. They say it does not have one, but in fact, to say that there isn't one is to say that there are many for you to choose from. So you can't choose one. One important theorem, and then you can prove that using epsilons and deltas if you are interested in that. But whenever f is differentiable, so when its derivative exists at a given point, then it's also continuous at that point. So there can't be a hole in the graph of f if you are able to find the derivative at a. There can be a hole at A, right? Or a jump, or an asymptote, for example. So what this is saying is that the converse is not true. If it is continuous, it may be non-differentiable. And an example is just this, right? This is continuous. You can draw this without lifting your pen from the paper, right? So it's continuous, but it's not differentiable at 0. Okay. So whenever differentiable, yes, continuous, but it doesn't mean that whenever continuous, we get differentiable. So you can expand on the question as to how a function cannot be differentiable. This is the first example. There's a corner, or a kink, or a cusp, whatever you want to call it, at that point. So that's a way. Another way is when you have a vertical tangent line, which means to say that the rate of change gets too large, just like with square root of x. So here's an example, so the blue graph right there. As you get closer and closer to that little cusp, your tangent line gets closer and closer to a vertical line. So infinity is not good for us. Same thing happens at the blue one. Right? So I have a vertical tangent line. It does have a tangent line, and it's vertical. However, because f prime goes to infinity, the slope is undefined. Okay, but it does have a tangent line. It's not differentiable, but it has a tangent line that's vertical. Okay, that's a possibility. Other three possibilities: if the function is discontinuous, there's no hope that it's going to be differentiable, because from what I said, right, whenever a function is differentiable, it is continuous. If I already know it's not continuous, I also know that it's not differentiable. Okay, take a second, stop to think about the logic behind this statement that I just gave. But that's a good way to sort of rule things out when you're investigating a function you don't know. So whenever there's a corner, right, a cusp or a sharp turn, people will say, or a vertical tangent or a discontinuity, your function is not going to be differentiable. Okay, it's not going to have a derivative at that point. Higher order derivatives, these are cool. If you start with a function, okay, and derive it, then you get another function. What's stopping you from just deriving it again? So if you do that, you get a second derivative of your original function. And here's Leibniz notation for it. You just add a 2. This confuses everybody, so don't worry that you get confused with this. You're eventually gonna understand everything. The d on the top goes onto d. The 2 on the top goes onto d, and the 2 at the bottom goes onto x, which is the variable. It's going to start to make more sense as you get to multivariable calculus. If you do, that just Leibniz notation. Most of the time in this class, at least, we're going to use f double prime is how we say it, right? Just 2 little lines, which just means that we derived f, found the function, so we derive it again. I'll do the example here, and you can see how that works. There's a pattern that if you can see it happening, it's going to be helpful for you. So let me go ahead and find the derivative of f prime of f first. So to find f double prime first, I need to find f prime. So f prime of x is the limit of f of x plus h minus f of x over h, as h goes to 0. So that's the limit of x plus h cubed minus x plus h minus x cubed minus x, all that divided by h. It just plugged in x plus h into f. That's the limit as h goes to 0, so that's the limit h goes to 0. Okay, so let's expand this. We can use a special product. A plus b cubed, that's a cubed plus 3a squared b plus 3ab squared plus b cubed. Or you can just manually expand this if you want, just FOIL it to find x cubed plus 3 x squared h plus 3xh squared. Okay, and then this one, minus x minus h, and then minus x cubed, and then plus x, all that divided by h. Should have practiced doing this a little bit at this point. So x cubed minus x cubed, sorry, it's moving too much, so that goes away. Minus x plus x, that goes away. Have a minus h, that doesn't go away with anything. Didn't we have, I think I forgot a term here, that's a b cubed. I think I forgot an h cubed over here, so there's a plus h cubed, sorry about that, right there. So that will be the limit. H goes to 0. I'll also take the liberty of factoring out an h at the top, because that's what we usually do, right? So that's going to be a 3x squared plus a 3xh plus an h squared minus 1, right, from this term right here. That did not cancel. Double check. All divided by h. So now I have the advantage. I can cancel this h out. And as h goes to 0, I can just plug in h equals 0. That goes away. That goes away. So I got 3. I'm not even going to write limit again. So that's 3x squared minus 1. So that's f prime of x. Okay, that's the first derivative that I have found. But that's not what I was asked. I was asked for the second derivative. So that's a little bit more writing now. So that's going to be f double prime of x. That's f prime of x prime, I guess, right? So that's going to be the limit as x goes to 0. So sorry, as h goes to 0 of f prime of x plus h minus f prime of x over h. So I get this formula that I just found. Let me go back and see if I didn't make a mistake. I think I'm okay. And I plug this guy into f prime. So that will be limit as h goes to 0, 3 times x plus h squared minus 1 minus 3x squared minus 1. All that divided by h. And I just manipulate this. Okay, so add a page. So now I get, this is the limit as h goes to 0. Can FOIL this, right? FOIL this or use a special product. So this is x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1, all that divided by h. Limit h goes to 0. Distributive property, 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1, all that divided by h. Cancel what can be canceled. 3x squared goes away with 3x squared. Minus 1 plus 1. Factor out an h from the top. So that's h times 6x plus 3h. Anything else? I think that's all. Cancel these two guys out. And now as h goes to 0, this goes to 0. So that's 6x. Okay, so I can write f double prime of x equals 6x. And I found the second derivative. Okay, so finding the second derivative just refers to the process of deriving twice. You're going to notice, I guess that's all the writing I was going to do. It's not that little writing as I thought it was going to be. Kind of a lot of writing. You're going to notice that our solutions for this class are enlarging, right? They're becoming much larger than you used to. As this class progresses, you're going to see that's going to be more common that you're going to take an entire page to solve a problem. So it's important that you master the minor steps that you need to understand to be able to solve these things. So you have to master what this is, what I'm doing here, right? and everything in between is just algebra. And then I got this. And now that I need to do this again, and then to find the answer at the end, everything in between is just algebra. So the algebra that we practice in 141 and 142, it's going to become sort of a minor detail in our more complicated solutions. Okay? And if you want to graph them both using the equations that we found, so this is f that was given to us, x cubed minus x. So x cubed minus x. The red or pinkish one is 3x squared minus 1. Just remember it from before. And this is f double prime of x equals 6x. This is the green one. There's interpretation to be made here, which is why they graphed it. Look at this. Start with the blue, right? And this interval, make it a little smaller. F is increasing, so f prime is positive. Yeah. Here, f is decreased. Let me continue with the green so I don't have to change. This is also increasing here, so f prime is also positive. Okay. However, on this interval, f is decreasing, it's going down, so f is negative. See that? Okay, so let's step it up a notch. Let me erase this, and let me do the same between f. F prime to f double prime. So f double prime is increasing here. So f prime is increasing in that first interval, and f double prime is positive because of that. F prime is decreasing here, so f double prime is negative because of that. Okay, how does that help me, right? What does it mean to say that f prime is increasing? So start with the blue line again, and now let's compare the blue straight to the green, and that's going to be the huge breakthrough we're going to talk about in the next few slides. So what's happening in this interval? So right here you have this guy as its tangent line, but as you move forward, the tangent line changes. So we have a positive slope, but then here you have a negative slope, and a zero slope, and then a negative slope. So the line is changing. The slope was positive and becomes negative. Okay? That's the same to say that the graph is concave down. That's something that's coming up. So if you don't understand it now, that's fine. But this is concave down. So the concave part of the graph, right? The graph is bending down, I guess. And that has to do with the second derivative being negative. Okay? I'm going to expand on this a little bit today, but most of this is going to be talked about later. I just want to poke your brain with this a little bit. Yeah, so they're doing exactly what I just did here, explaining. Here's the, I guess, interpretation of these higher order derivatives. When you start with a position function, always remember this, okay? This is the main example that people are going to give to you when you talk derivatives, and the example that if you're able to talk about, they're going to think that you know what derivatives are. And in fact, that helps. So if you start with f as the position function, then the first derivative is the velocity. V equals s prime of t, okay? Gotta remember this. The derivative of position is velocity. If you derive it again, you're looking at how fast the velocity is changing. So the rate of change of the velocity. So that's the acceleration, okay? So basically, a of t equals v prime of t, which is the same as s double prime of t. So The second derivative of position is acceleration. So basically, you're measuring, is your velocity increasing or decreasing? How fast is it increasing? How fast is it decreasing? Right? Okay. So just think about it when you're driving and you don't have anything, you don't have your foot on the gas pedal. The car is decreasing velocity, so the acceleration is negative. The second derivative of position is negative. The position is still increasing because the car is still going forward, but the acceleration is negative because you're losing velocity. Okay? If you really pump the gas, like hit the floor, then for sure the velocity is going to go up, is going to start to go up. So that means acceleration is positive. Okay? So the second derivative of position is positive. Okay, now you can try and repeat this process and find the third derivative. That's fine. It works the exact same way. Just look at where the 3 goes here. Doesn't matter much in this class at least, but it's going to matter if you go into multivariable calculus. Most of the time we'll just write it as triple prime. Okay. Sometimes you also see it as f with a little 3 here of x. And that way it's easier because if you want to do like the 100th derivative, then you know it's just a little 100. Don't have to draw 100 little lines. But it's just the same process. Just find the derivative and just do another limit. If you want to do velocity, position, velocity, acceleration, the next derivative is the jerk, right? That's how you call it. It's the jerk because then you're measuring how acceleration is changing. So if you go back to my analogy of if you don't have your foot in the gas pedal, then acceleration is negative. But if you hit the floor, then it's positive. How you're changing your foot, right? When you move, as you're pushing, the movement of pushing is what's somehow associated to the jerk. Yeah. When you move from your foot off the pedal to hitting the floor, that's positive jerk because acceleration is increasing. And when you move backwards, when you're hitting the floor and you're removing your foot from the pedal, that's negative jerk because acceleration is dropping, is decreasing. And the jerk is the third derivative of the position. The first derivative of acceleration and the second derivative of velocity. Okay? The name jerk is just because it's very sudden and abrupt movement. When you do that, right, when you just hit the floor, the larger the jerk. And it has to do with, again, traffic and vehicles again. And there you go. And they're introducing the notation I mentioned. If you want to go like the fourth derivative, usually you do this rather than drawing 4 little lines. And you just derive it as many times as you need. Just keep repeating the limits over and over again. This is what I wanted to talk about today. We did an example of finding the second derivative. We talked about a bunch of concepts. So I do recommend that you have this all in writing. Stop, maybe read your notes again. Think about all this. Read the book. And make sure you understand what we talked about because we're going to build on this. And we're going to start to use these derivatives and these names to say geometric things about the graphs of functions as we go on in this quarter. Thank you for bearing with me.